So our next presentation is going to be given by Hyungjin Chung from Korea, currently lead AI research scientist at Everx, which is a medtech startup in Korea. Hyungjin did his PhD at KAIST, supervised by Jong-Chul Yi. Many of you will have heard of Jong-Chul Yi. And later on this year, he'll be joining the Department of Computer Science and Engineering at Korea University as an assistant professor. Hyungjin is a major pioneer, I would say, in the use of diffusion models and their use with inverse problems and image reconstruction. In fact, I just checked yesterday your 2023 ICLR paper entitled Diffusion Posterior Sampling for General Noisy Inverse Problems now has over 1,500 citations. And this year it's looking like it's going to be cited 1,000 times based on my estimates. So that's a very impressive contribution right there. So today he'll be presenting on how to adapt diffusion models when your test time data is different to your training data, how you adapt those in the context of medical image reconstruction. So thank you so much for joining us today. Over to you, Hyungjin.
Yeah, thank you, Andrew, for the very nice introduction. I'm Hyungjin. And today I'll be speaking a bit about using diffusion models for inverse problems, but more about adapting them when we have unexpected out-of-distribution measurements. Yeah, so over the past years, we've seen quite a lot of advances in diffusion models themselves. Computer vision folks have a strange tradition of measuring the advances of diffusion models through a video of Will Smith eating spaghetti. It kind of advanced a lot over the 2.5 years of research. And it's, along with the advancement of the diffusion models themselves, now people in the inverse problem field are acknowledging more and more of using these diffusion models for various types of image restoration and reconstruction problems. And if you've used Google's Nano Banana Pro, you can edit an image or you can synthesize an image with that. Under the hood, if you ask the model to generate a 4K resolution image, under the hood it uses a diffusion model to actually upscale the image to 4K. So it's being used a lot in various domains. But to us, generative models, and especially among them diffusion models, are pattern matchers. It's a way to train a good prior from empirical data samples. And diffusion models they seem complex, but they're actually denoisers trained with various noise levels such that once they are trained, you can use them to iteratively denoise, starting from a Gaussian noise and at the end acquiring a good high fidelity sample. One another advantage of diffusion models are that they can be interpreted as score functions, time-dependent score functions, which are by design a score function of the prior, but in a blurred sense. And if you try to visualize the reverse process of generating an image from Gaussian noise, the reverse diffusion sampling, this is how it looks like. You can do this either through an SDE or solving an ODE. But for us, we don't really want to get a random sample from a diffusion model. We typically want to sample from the posterior, where you have a measurement y, and we want to sample a good image that respects this measurement process. And today I'm going to talk mostly about MRI reconstruction and CT reconstruction as their representative examples of linear inverse problems in medical imaging. So if you just write down the probability flow ODE formulation of diffusion models, this is what we have. And since we assume that we have a good pre-trained denoiser, we can solve this ODE, and what we will get is this good image that looks like this. And now if you want to sample from the posterior, all you have to change is that instead of the score function of the prior, we now have the score function of the posterior. And interestingly, due to a thing called Tweedy's formula, we can write this again in a different way where it's not dependent on the score function, but it's now dependent on the conditional posterior mean. before I delve into how we use this to adapt diffusion models to OOD problems, I'm just going to do a brief background on how you generally use these diffusion models for solving inverse problems. In order to achieve conditional score function, you have this Bayes rule, and we can swap the score function with the prior with the pre-trained diffusion model, but the problem is with this time-conditional likelihood function. The reason being is that if you would like to compute this value, you would have to marginalize out the reverse diffusion process for every time step t, which would be intractable. So a widely used approach called diffusion posterior sampling is to try to push the expectation inside such that now the computation is just a single step of neural network call. And when you try to implement this in practice, here's how it looks like. Starting from a noisy image during the reverse diffusion sampling process, you query a diffusion model to denoise it. You push it through for a measurement model and try to minimize the to maximize the measurement consistency. And you do a gradient backpropagation. The advantage of using diffusion models is that it's very easy to implement. It's just a one-liner change to your usual prior sampling code. And it's useful to think about all these different types of posterior samplers using diffusion model in two different ways. You can either think of this as an approximation to the conditional score function, but at the same time, you can also think of this as an approximation to the conditional posterior mean. And under those interpretations, there's another sampler that I would want to mention. It's called the decomposed diffusion sampler, where instead of doing gradient update steps, you actually try to approximate the conditional posterior mean through a proximal optimization problem, which is given in the closed form, such that you don't have to follow backpropagation through a neural network, which makes this sampler usually much cheaper than DPS. And some of the main applications that I have with DDS is in multi-coil MRI. But let's say you wanted to expand this to solving 3D inverse problems, which is often the case in medical imaging. So what you would typically do in these cases is that since it's very hard for you to train a good 3D prior out of the limited samples and under limited compute, what you would typically do is you would take your diffusion model trained on slices of images, and you would try to make this into a factor prior by incorporating other priors. For example, a widely used total variation prior, such that it imposes some smoothness to the other axes. And so how this works in practice is as follows. You do the posterior mean estimation in the usual sense. But in this case, if you do this, you would get independent samples across this dimension. So what you would do is you would run an optimization problem that additionally imposes some total variation prior or some variant of this. And through that, we're able to achieve this impressive reconstruction result even from a very limited sparse few CT samples. Moving forward, we actually have another approach that even improves this performance even further for 3D imaging. In the former case, we used a total variation prior for one of the factor priors. But in this method of TPDM, we introduced a diffusion model prior for both of the planes, so that during inference, you're free from using this optimization approach of using to incorporate TV prior. You can use just iterative diffusion model in an interleaved fashion, so that at the end of the day, if you want to use it for reconstruction, you can use it for that. And if you want to generate 3D volumes, you can also do that. So these are samples that are generated from a 3D diffusion model. Well, it's not 3D, but factored 2D diffusion model, which looks quite a lot like real volumes. So I've discussed several methods for solving inverse problems with diffusion models, But it's important to note that most of the diffusion model-based inverse problem solvers out there in the literature, they can be seen as some form of explicit approximations to the conditional score function. Yeah, so that was a bit of a long introduction, but the main content of today that I want to discuss is using diffusion models for out-of-distribution test data. This might be a bit of a stretch, but as a conceptual example, let's say that you have a trained prior that are trained only on dog images, but at test time you get measurements that were actually derived from cat images. Well, this happens all the time in practice, actually. It's just that there's a degree of how severe your out-of-distribution measurements are. And one example that I like to talk about often is the black hole imaging case, where you never have access to one ground truth image, since all you can do is you can sparsely sample the case-space magnitude in the same exact place of the case-space matrix, and so that your problem becomes, given all these sparse measurements, you can't train a good prior, so that all you can do is maybe you can train your diffusion model on phantom data, and hopefully this diffusion model will achieve some generalization such that even if you have this prior mismatch, you can get a decent sample. We can actually apply this idea to the medical imaging case, since also in medical imaging there are lots of cases where we don't have this perfectly gold standard data, a lot of gold standard data such that we can train a good diffusion model from. So let's say we have these images of ellipses that can be generated on the fly, so that you can generate infinite amount of training data with this. And if you try to train a diffusion model and try to use this diffusion model to reconstruct from sparse view CT, this is what you would get. And this looks very bad, since the reconstruction emulates this these artifacts that from the training data, and we wouldn't want this in practice. So when you have this kind of problem where you have a single measurement that you have no idea how this stemmed from, we can think of using deep image prior, where the idea is that if you have an untrained network and you have a single measurement data, you can try to overfit this network to the single measurement through the data consistency loss. And now we attempted to extend this to deep diffusion image prior, where we have a diffusion model pre-trained on out-of-distribution samples. But now we're going to adapt this diffusion model with this loss, where d of theta is different from g of theta here, in a sense that this is not a feed-forward reconstruction, but this is some form of estimation of the conditional posterior mean. So this can be either DPS, DDS, or any of the other approximation methods that I alluded to earlier. And now this process doesn't iterate on a single XT. It's gonna run the adaptation on the fly during the reverse diffusion sampling, such that it starts from Gaussian noise. But as we progress through the reverse diffusion sampling process, this estimate d theta of xt given y is gradually becomes more exact towards your reconstruction. So iterating that process, we have the algorithm called DDIP. And so the algorithm is actually very simple. During the reverse sampling process, you update your network parameters of diffusion network parameters with this minimization problem, and then you update your usual, and then you do a single reverse sampling step. So you can do this on the fly. One of the crucial components that we found to be important on maximizing the performance of DDIP was the use of the same conditional posterior mean estimate for d theta of t. So there's this previous work called steerable conditional diffusion. A lot of the people ask what the difference between DDIP and SDD is. The difference is that in SDD, the work used a different d of theta t for the network parameter update step and the reverse diffusion sampling step. And we found that that's not a good idea. It's very important that you try to use a consistent estimator for these two steps. Right, so let's compare DIP and DDIP. One downside of using DIP is that while it works well in several practice, one of the problem with diffusion deep image prior is that it requires quite long optimization processes, and it often fails if you don't properly early stop this process. And compared to that, since deep diffusion image prior starts from a good initialized estimate of the prior, and it does a multi-grid generalization of deep image prior, it tends to be more stable. And if you try to run different variations of hyperparameters, DDIP tends to work better generally. And since we're doing, in a sense, a continual learning from a pre-trained network, it's usually a good idea to use low-rank adaptation such that we don't alter significantly what the prior had beforehand. And so this is the general result that I have comparing DDIP against these different methods of non-adapting diffusion model solving. And we can obviously see how the previous methods heavily overfit to the prior, whereas DDIP has a good reconstruction quality even in the out-of-distribution sense. Now, since I talked about 3D imaging before, it's important to try to devise a method where we can easily use DDIP for 3D. Since DDIP was devised for a single measurement, one might think that it's enough to use DDIP for each measurement independently. But then again, we have this consistency problem. And this is going to cost a lot since the adapting process is usually slower than the usual reverse diffusion sampling. So one way to cut on the compute cost and achieve better generalization is to use the so-called D3IP, where you keep a single track of the theta volume parameters such that this parameter can be used for all the different slices, and the adaptation process can be run with Monte Carlo samples from the same volume. And this type of process reduces the computation from O of nt to O of t such that it runs much faster. And this is one result of using D3IP in the process. And if you would truly want to squeeze out the maximum performance, we additionally propose a meta-learning variant of DDIP where you don't simply keep track of a single parameter for the whole volume, but you actually update a few more gradient update steps to each of these slice-wise parameters, which results in a slightly improved performance. Now, the previous method that I talked about, DDIP, and all those variants, were the experiments there were mostly focused on inverse crime, where we usually tested with the simulated measurements. And now, in the follow-up work, we tried to extend this to a real-world imaging case where the problem was super resolution of the 3D CT scans, and we had no way to acquire a high-resolution CT scan in the z-axis, so this neurosurgeon wanted us to super resolve it in the z-axis. But obviously, since we don't have high-quality data, we had to use some out-of-distribution training data, so we went ahead and tested how we could use this D3IP idea to these kind of measurements. And here we kind of tweaked our algorithmic process, again, kind of resembling TPDM, where I noted that you can, in theory, use two different diffusion models, one for the primary plane where you do the super resolution, and for the auxiliary plane, So you iterate between these two diffusion models. But since the primary plane is trained with out-of-distribution measurements, we additionally adapt this process with the DDIP. And for the auxiliary plane, since these are in-distribution samples, we can simply use reverse diffusion sampling or do score distillation sampling gradient update steps, which we did in this work. And so here are some of the results. Since we don't have a ground truth skull data for this data set, we can't really do quantitative evaluation, but from what it looks like, it definitely does a better job at restoring this, this volume, especially seen from the 3D render. And we went ahead, tried to, since we couldn't do quantitative evaluation on the actual in vivo data, we went ahead and tried to simulate this to try to see if how much we can push the adaptation process under when we have the oracle. And so if we compare the performance of this DDIP against the oracle case, where we have two in distribution diffusion model, we actually come very close to achieving this gap. So before I end this presentation, I do want to mention several different category of methods that are very related to this DDIP work. So recently, there are many works that try to train a good diffusion prior from measurements that are sampled from this likelihood function. So there are different approaches, but if you try to group them into several, we could say that there are Shor-based approaches, there are expectation maximization-based approaches, and there are also a family of this called ambient diffusion. These three groups propose different ways to train a good diffusion model from measurement data only, given that the measurement data are acquired from different instantiations of the system matrix A. And now there's another group that proposes some equivariance regularization, such that even if you have measurements acquired from a single system matrix A, you can actually try to train a good diffusion model out from only the measurements. But I want to note that the DDIP or SCD, these methods are quite different from what these methods are proposing. So these methods are proposing a way to train a good general prior from the measurement data. And in contrast, DDIP is a method of trying to overfit or adapt your diffusion model on a single slice or volume of measurements. So I think one good potential research direction would be try to marry these two different types of training diffusion model with measurement ideas so that we can achieve further complementary gains. And yeah, with that, I would like to take any questions you might have.